All right, so start off, my talk is about sharing today. That might be, I don't know if I can turn this down at all. Simplest way. So you all can still hear me, right? All right. So my talk is about sharing today. So I guess I should start off by what do I mean by sharing? Well, sharing is the exchange of information among users. And this can be non-computer based, such as passing around notes at an in-person meeting, or computer based, such as sending out that same set of notes by email. And we'll be focusing on computer-based sharing today. And there are many domains of computer-based sharing, some of which are asynchronous, such as email, distributed file systems, and communities, and some of which are synchronous, such as instant messaging, application sharing, and virtual worlds. And in each of these domains, users must address what we call is the user selection problem, or deciding with whom to share this information. In email, this is done by specifying recipients of some message. Distributed file systems, this may be done by specifying rights for shared objects. Communities, you may do this by specifying privacy rights for shared posts. And instant messaging, you may do this by selecting contacts from a recipient list, from a set of contacts to send some instant message. And as certain well-publicized examples have shown, addressing this problem is difficult. 9/11 was not prevented, at least partially because information was not shared with enough people. Afterwards, the US government went in the opposite direction, where an individual had access to more information than was necessary, leading to WikiLeaks. And these both show issues in distributed file systems, but they're not limited, are not limited to a single domain. For example, in the domain of email, Michelle Bachmann was accidentally addressed in an email critical of her. And in the domain of communities, a survey of the top 150 Facebook apps found that 91% of those apps were unnecessarily given access to private data. And this is actually part of a more general problem of selecting items from a list of options, where the main issue in this general problem is human memory, where users must recall all possible options, whether that be digits, letters, words, email addresses, so forth. And users must also recall whether to select each of these options. And past work has identified specific issues in this general problem, namely that users could only correctly remember a limited number of digits, letters, or words, or users could only specify a portion of known binary or ternary features of phonemes correctly. If we apply this to our problem, where we treat whether to include an item or not as a binary feature, it's likely then that users will not correctly specify those binary features, where they may not include some things they should, and include some things they should not. So the next question is how to address these issues. Well, one obvious approach is to offload to computer memory. For example, you could have a list of options which users could read through and then select things as they view them. And this is the approach used in many email clients, such as Gmail and Mozilla Thunderbird. A more subtle approach may be to group options, and this is based on the idea, or the observation from past work, that users more easily remember grouped rather than ungrouped items. For example, it may be very difficult to remember all of these characters, but if you then group them into words, it becomes much easier to remember them. Moreover, you can make binary decisions of whether to include things or not at the group level rather than the individual level, therefore making fewer decisions. So for example, we could decide to include all of the characters from Monarchy and none of those from Big, rather than each individual character. We can also go beyond this by grouping on multiple dimensions. So some work has grouped with whom items are shared, or subjects, and items that are shared, or objects. And here's an example interface that displays these, which Mike Reiter was a part of. So we see in the columns on here, these are individual subjects that can be shared with, and groups of subjects, and objects that can be shared, or groups of objects or folders. And in each of these approaches, there's required user effort, offloading memory and grouping individual options. So in offloading memory, users must exert effort to transfer data to and/or retrieve data from the computer. To illustrate, there's the Enron email corpus, which is a collection of about 130 email accounts from Enron executives. And on average, each of these accounts had 524 contacts. And in a survey of Facebook, a past survey of Facebook found that on average, users had 130 friends. So users in these systems would have to upload information specifying these contacts or friends. And if they use the read from a list option, they would have to read through 524 contacts or 130 friends each time they wanted to share information. Also, in grouping options, users have to exert effort to create, populate, and maintain groups. And the larger the number of users there are, the more effort it is to create, populate, and maintain these groups. So we see that effort increases as scale increases. And in some sharing domains, namely the email and communities domain shown here, some domains have large scales that lead to significantly high effort. And with this high effort comes trade-offs. Because past work has observed that users tend not to fully solve an information security problem if by doing so, they're better able to complete other tasks. For example, a common problem that users have to address, or a task people have to complete, is decide whether to grant access to some executable in Windows. Users may not fully solve this by always clicking yes or always clicking no. If they always click yes, they grant access to a malicious program on the left. If they always click no, they don't grant access to a beneficial Java IDE on the right. These trade-offs may also explain certain observations in information sharing. For example, users chose not to share possibly helpful health information on Facebook. Users do not spend time learning how to use friend lists on Facebook. Most mobile users do not use existing functionality to group their contacts. Past work has observed that a large portion of emails do not correctly contain a desired recipient. For example, a homework submission may be only sent to a professor when it should also include the TAs. And students in a UNC class sent emails to the class listserv rather than the TA and instructors listserv. So this might be some email about missing class for some sensitive health reason, and it was sent to Comp 401 rather than Comp 401 help. And we might think this is just a problem when it comes to students who don't really know any better, but faculty make this mistake too. So a recent email was sent to tenured faculty about a phased-out retirement program, and it specifically stated, please do not respond to this email, because responses would be sent to the original recipient of this email, original recipients. But despite this fact, many people responded with sensitive information about their ages. And this shows private data was unnecessarily shared, and spamming of individuals, which past work has stated is an information security problem. So how can we reduce this effort? Well, one approach is full automation, where the system automatically performs user selection without input from the users. So this is good in that it requires no effort from the user. But users do not correct the system as it is wrong, therefore allowing through possible errors. An alternative is a mixed initiative approach, so called because both the user and the system take initiative in exerting effort. The system initially exerts effort by identifying likely tasks, such as suggesting recipients in an email message. Then the user exerts effort by accepting, editing, or rejecting these tasks. So in this example, the user may select some of these suggestions that are appropriate. Then the system finally exerts effort by performing these accepted or edited tasks. For example, taking those suggestions and adding them to the set of recipients for this message. In other words, this approach generates recommendations. And this is good in that the system performs most of the effort, but the user can modify or reject incorrect tasks, therefore blocking some possible errors. And this is the focus of our work. However, this mixed initiative or recommendation approach is not applicable for all domains. The domain must have a past record of sharing, and this is necessary to train, test, and compare different recommendation schemes. The domain must also have large scales that cause high effort, and this is not likely, these large scales, unless there is an asynchronous collaboration. And among the many domains I've touched on today, email, communities, distributed file systems, instant messaging, application sharing, and virtual worlds, only 2 of these fit these requirements, so we'll be focusing on those 2. And this gives us our overall thesis. It is possible to make predictions in email and communities for addressing the user selection problem in large-scale computer-based sharing that will require less user effort than past prediction techniques or cases with no predictions. So now that we're generating predictions, the next question is, well, when should we generate these predictions? Well, we can think of it as a timeline of when a user wants to share a particular piece of information, where at some point the user begins choosing with whom to share information, and at another point the user actually shares that information. So we've really divided this timeline into 3 different parts. And we first tackled this problem by addressing this middle section, by helping users choose with whom to share information. And we did this by providing recipient prediction. Well, what is recipient prediction? Recipient prediction suggests full recipients for shared information. And this is in stark contrast to recipient completion, because recipient prediction requires that no portion of the recipient be entered before the recommendation, while recipient completion requires the user enter a prefix for the recipient, and then the system recommends completions to that prefix. So why is recipient prediction helpful? Well, it will address certain observed issues that we've already touched on, such as forgotten recipients by suggesting additional recipients, or entering incorrect recipients by suggesting the correct one. So there is some past work in recipient prediction, and it can be divided into two spaces. Group-based, which bases its predictions on sets of recipients in past and current messages, and content-based, which bases its predictions on text in past and current messages. And to illustrate how this works, let's look at an example. So some student, Chris, is emailing out a CS question. He's already addressed Albert, but in the hopes of getting his question answered, he wants recommendations of who else he can send this to. For these recommendations, we can look to some messages from fall 2011 and spring 2012. Group-based, we'll look at the group Chris has already addressed, which is the individual Albert, and we'll look for similar groups in past messages, i.e. those that contain Albert. Content-based, we'll look at the text or words that are in the current message and look for similar text or words in past messages. So for example, we may look for words that, messages that contain the words CS or question. We then wanted to evaluate this past work. Particularly wanted to know, how do these approaches compare? And there's actually been no consistent evaluation to compare these group-based and content-based spaces. So we compared using a common model and data set. We used the Enron email corpus, which is a publicly available data set, and we recommended at most 4 individuals or recipients at a time. That's because this is the state-of-the-art done in Gmail actually right now today. And in order to do this comparison, we also need to know how much effort do the predictions from these spaces require. And in order to determine that effort, we needed certain evaluation metrics. And first, we looked at past work, at what metrics they had used. And they used classical metrics, precision and recall, where precision measures the percentage of lists with a correct prediction. Therefore, predicting we should have more recipients correctly, but not providing correct predictions. So it's a sense of false positives. Recall, on the other hand, measures the percentage of lists that are not empty. We could say an empty list indicates that there should be no more recipients, so that's incorrect and gives a sense of false negatives. As we can see, these metrics measure accuracy of recommendations rather than reduction in user effort. So we want to know, how can these be related directly to user effort? To see how that might be done, let's look at a model of how users interact with these recommendation lists. So at some point, a list of recommended recipients is generated. If this list is empty, the user must manually enter a recipient. If it is not empty, we assume the user scans that list. If there is not a correct recommendation, the user must manually enter a recipient. If there is a correct recommendation, we assume that the user will click that correct recommendation. If this set of recipients is complete after the user manually enters a recipient or clicks a correct recommendation, we assume the user stops addressing the message. Otherwise, a new list is generated and the process completes. So this model takes into account precision and recall, or P and R, where R represents whether a list is empty or not, and P represents whether a non-empty list will have a correct recommendation. We also have certain effort measured in this model: scans, or S, clicks, or C, and manual entries, or M. Because we assume each non-empty list is scanned, we assign S is equal to R. We assume that each non-empty list with a correct recommendation is clicked. C is equal to P times R. And each time a user does not click a correct recommendation, they must manually enter an item. So M is equal to 1 minus C, or 1 minus P times R. So we then can compare our content-based and group-based approaches with these scans, clicks, and manual entries. And we see that scans are roughly the same across the two approaches. Groups require more clicks, and content requires more manual entries. So which approach is better? Well, no approach is better with respect to all metrics, so we really need to know which metric requires the most effort. So to do that, let's take a little bit closer look at what these metrics, what these types of effort actually mean. In scans, the user must parse and identify a correct prediction in a list. In clicks, a user selects a pre-identified correct prediction. And in manual entries, a user must remember and type the full email of a recipient. Based on these definitions, we judged manual entry to be the most effort, clicks to be the least effort, and scans to be somewhere in the middle. Based on these rankings, we judged groups to perform better than content. However, they are not perfect because they require some effort with respect to all of our metrics. So we wanted to know, can we improve upon the group-based predictions? And in order to do that, we asked the question of, can the group-based approach be extended to generate more effective recommendations? But before we can go into that, let's get a better understanding of the group-based approach. So recall, recommendations in the group-based approach are based on groups and past messages. And groups must be the full set of recipients for some past message. To illustrate, let's look at our example messages from earlier. Albert and Eddie are a group because there is some message that contains them as the full set of recipients. Albert, Eddie, George, and Sue is also a group because there is some message that contains them as the full set of recipients. However, Albert, Eddie, George is not a group because while there is some message that contains them as recipients, no one message contains them as the full set of recipients. Then individual recipient predictions are ranked based on the groups of which they are members, where the rank of an individual is the sum of ranks of groups of which that individual is a member. Mm-hmm. So Albert, Eddie, George is contained in this message, but it's not the full set of recipients. So there's another recipient. Yeah, so Albert, George, Sue would be a group. So then we can rank groups based on an IR score of the set of messages M which contain that group, where an IR score is defined by the following formula. This IR score takes into account whether messages are sent or received and assigns sent messages some sent importance. It also takes into account time by exponentially decreasing the importance of older messages using a standard half-life formula. Past work also went beyond this by providing context of the current message. In particular, it looked at the seed, or the set of already addressed recipients in this current message. And this seed may be from manual input, previous recommendations, or maybe some combination thereof. And then we actually can rank of an individual is not just a summation of ranks of groups, but a summation of seed scores, where a seed score is the function of the rank of the group, the members of that group, and the members of that seed. So how can we calculate this function of the rank of a group, members of the group, and members of the seed? Well, past work used intersections, where some members of the seed must be part of the group. So the rank of the group was multiplied by the size of the seed. So if there was no intersection, the score would be 0. But the larger the intersection, the larger this value would tend to be, meaning the more members that have already been addressed of some group, the higher the score tends to be. So we modified this to instead use subsets, where all seed members must be part of the group, therefore requiring a stronger link between the seed and the group. And so we came up with our own formula, which was matching somewhat, where if a seed is a subset, if a seed is not a subset of the group, the score is 0. Otherwise, we'll multiply the rank of the group by the size of the seed divided by the size of the group, or the percentage of the group that is made up of that seed. So therefore, the more members that are already addressed from that group, the higher the score tends to be, which matches past work. Yes? So that's the IR score, which is a combination of sent and time and total number of messages. So we then evaluated these intersection-based and subset-based approaches in terms of scans, clicks, and manual entries. And we see that they're roughly the same in terms of scans, clicks, and manual entries, but subset-based required much fewer scans, or required roughly the same number of clicks and manual entries, and subset-based required much fewer scans. And this means we're generating fewer non-empty lists containing all incorrect predictions. So based on this, where all metrics were either about the same or less than the intersection-based approach, when we look at subset-based, we judge subsets to show less effort than intersection. So the subset relationship between groups actually means we can build a hierarchy, where groups of subsets relationships can be organized into a hierarchy. So the leaf nodes of this hierarchical tree are individuals. Their parent is a superset of them, and the next parent is again, superset of that. And from this hierarchy, both leaf and intermediate nodes may be selected. So current work has just allowed the selection of leaf nodes, but it may be helpful to select the Albert and Eddie together, or Albert, Eddie, George, and Sue all together. And the success of our subset-based approach suggests that users are building up these hierarchies anyway, so selecting intermediate nodes would be useful. So our next goal was how to identify and present these intermediate nodes. And to do that, we had certain goals in mind. Namely, we wanted to be composable with past flat approaches. And this is because we wanted to make use of the successes of past prediction schemes. They didn't provide these intermediate nodes, but they did show to reduce effort in many cases, so they seem to be good predictions. So our goal was to take existing flat lists and sort them into hierarchies. We also wanted to make no large changes to the user interface. This would be so we can be comparable with past work. So current state of the art presents lists as a flat horizontal linear list. And so we made a slight modification where we include markers within that list to indicate hierarchical groups. So Alice, Bob, and Chris are each selectable individually, but you can select the group Alice and Bob by selecting corresponding parentheses or other marker, and Alice, Bob, and Chris similarly by selecting parentheses or other marker. We also want to present the best groups. And to explain what I mean, let's look at an example. So we may have this Alice, Bob, and Chris list that's generated by some flat approach, but we have a likely group Alice and Chris. To present this with our marker approach, we need to move Chris, allowing reordering, to allow Alice and Chris to be placed next to each other and thus inside parentheses. We also want to avoid presenting spurious groups. So if we have some ranked groups, the top ranked group is some large group Alice, Bob, Chris, and David, and its subset groups are much lower ranked. We may not want to present that lower group, because if we just present the large group, it's relatively easy to scan, but adding these extra possibly spurious groups, it becomes much more difficult to scan this group. So because they're less likely, we don't want to present those. We also want to add minimal scanning cost. And to do this, we looked at two possible cases, whether we would allow no partially overlapping groups. So to illustrate what this means, if we have a flat list, we would allow both Alice and Bob grouped together and Alice, Bob, and Chris, because the group Alice, Bob, and Chris completely overlaps with Alice and Bob, because that's part of the hierarchy. But partially overlapping groups would allow that same hierarchy, but maybe that same grouping scheme, but possibly Bob and Chris being grouped together. And we can see on the right that it's much more difficult to scan this and identify which parenthesis goes with which group, and thus make correct selections. So we won't allow the second case because that adds much more scanning cost. And recall that we have lists of at most length 4 coming from our flat recipient recommendation schemes. So this means we'll have at most 6 markers or 3 groups in our lists. And generally, for any list of length n, you can determine the maximum number of groups in a non-partially overlapping groups, and that's the maximal number of markers you'll add to any one list. So based on these requirements, we generated the following algorithm. And rather than go into the code, let's explain in detail through an example. So here's a flat list generated by some flat approach, and it's also ranked groups that it generates. Initially, for the hierarchical approach, we start with an empty hierarchy and an empty resultant recommendation list. So we start by adding the first highest ranked individual to our hierarchy. He can't be grouped with anything else, so we then add the next individual. So now there are 2 individuals in our hierarchy, so it might be possible to group them. So we look at their highest ranked group of which they are a member. Albert's highest ranked group, which is just Albert, is a subset of Eddie's highest ranked group, Albert, Eddie, George. So that means they can be grouped together because they share this subset relationship. And we'll group them of the superset of these 2 groups. And this means that our recommendation list has a group of Albert, Eddie. So we'll then add George to the top level of this hierarchy next to this group up here. because Albert and Eddie can't be merged any further. George's highest ranked group is a subset of his neighbor, which means we can group him down inside this level, putting him next to Albert, Eddie, and George, meaning we can select them all together. However, we might be able to do this recursively and add more groups at lower levels. So we first look at Eddie, whose highest ranked group he's already immediately under. So we can't move him further down in the hierarchy. But Albert, and George are not under their immediate highest ranked group. And Albert and George's groups also share a subset relationship, which means we can group them under the superset of these two groups, forming a third level to our hierarchy and giving us our final recommendation list of Albert and George grouped together and Albert, Eddie, and George grouped together as well. So our next goal was to test this hierarchical approach. And to test this, we again use the Enron email corpus, and this is to make it comparable with our flat evaluations. We also needed to model recommendation selection. So for example, if a user wants to select Albert and George from this hierarchically grouped list that we formed earlier, we could model it as random selection, where the user randomly selects some item. Maybe they select Albert first, and then hope that some other list is generated that contains George. But users don't select things randomly. They tend to have certain goals in mind. And they may have a goal of reducing effort as much as possible, which means they will select the largest correct recommendation. And that means they'll select both Albert and George together and not have to deal with any more lists. So we went with this, our approach assumed the second case, because we assumed users wanted to reduce their effort as much as possible. We also need to revisit metrics. So recall we had SC and M, or scans, clicks, and manual entries, in terms of P and R, or precision and recall. So each of these metrics assume that each click accepts one address or recipient. But this isn't the case if we have hierarchical, because we can accept 2, 3, 4, or more if we have longer recipient lists. So how can we adjust these metrics to take into account that each click may accept more than one address? To do this, let's let A equal the expected accepted recipients per click, and let X equal the total number of recipients. Of all lists scanned, P will be clicked. So P times S is equal to C. All recipients must have been clicked or manually entered. A times C is the total number of recipients accepted through clicks. M is the total number of recipients manually entered. So those two summed together are equal to X. And R of all lists will be scanned. So each time a user clicked or manually entered, they implicitly requested a list. R of those times, there will be a non-empty list. And so that result will be equal to S. We then solve for S, C, and M and normalize with respect to X to give us the following formula. And we then, as a sanity check, set A equal to 1, or assume that each click would accept one recipient, matching it to the flat recipient case. And we see that our formula matches the previous case, giving support for our new derivations. So we then compared non-hierarchical results and hierarchical results in terms of our new A, S, C, and M metrics. And again, we also, because they're not dependent on subset-based or intersection-based, we can feed both types of lists into these hierarchical approaches. We see that manual entry is slightly reduced, but scan and click costs are also reduced in the best case, even more so. So based on the fact that all metrics were reduced, we judged hierarchical to be better. And this is particularly good because we see that A value is much higher than 1, indicating on average users tend to accept more than one recipient with each click. Recall that our metrics are determined analytically and normalized with respect to the number of recipients addressed. Based on Diane Kelly's suggestion, we looked at other metrics that are measured during prediction or replay of prediction. In particular, we looked at the Gomes model, which had 4 metrics we were particularly interested in. Mentally prepare, which measures the times in which a user has to think about and decide on what action they're going to take. Clicks, or times in which a user has to press the mouse. Key presses, or times in which the user has to type on the keyboard, press a key on the keyboard, and switches between mouse and keyboard or vice versa, when you're already working with the mouse and move to the keyboard or vice versa. Mentally prepare seems to match the scans because we're mentally preparing and deciding whether to select things or manually enter. Clicks seem to match the C. Key presses seem to manual entry, and switches between mouse and keyboard were not captured in our model. So we then wanted to adapt and normalize these metrics to compare to our own. So we generated the relative scans, relative clicks, relative manual entries, and relative switches. And I call them relative because in each case they're divided by the number of recipients addressed in a particular message, and then they're averaged across all messages. We then replayed these predictions to capture these new metrics, where scans were captured each time there was a non-empty list of predictions. Clicks occurred each time there was a non-empty list with a correct prediction. Manual entries occurred each time a list, empty or non-empty, contained no correct prediction. And to measure switches between clicking and typing, we built a state machine, where initially in the first state, users start using predictions. Then they move from here to either clicking a prediction or manually entering a recipient. And because they deal with many, many lists, they can switch between these states or stay in these same states. And at some point, the user completes addressing recipients. In the click a prediction state, they're actually in a clicking state. In the manually entering a recipient state, they're actually in a typing state. And we assume that in the starting using prediction state, they're in a typing state. So we then measured switches between clicking and typing or vice versa, when they would switch between a typing and clicking state or clicking to typing. We then replayed our non-hierarchical and hierarchical models with these new metrics. And we see that scan, clicks, and manual entry values are similar and similarly reduced to our SC and M values. But they're not exactly the same, and this is likely because of noise. P and R, which we computed our SC and M values from, were computed across all messages, which means that they're not exact for each possible message. So some messages may differ. We also see that switches are somewhat increased. So we need to do some ranking again in terms of which metric requires the most effort. We assume that manual entry is a higher cost than switching because it involves remembering and then entering multiple keystrokes, while switching between mouse and keyboard involves one sort of movement from one to the other. So therefore, we still judge hierarchical to be better, which provides more support for our previous claim. And this gave us our first subthesis. It is possible to hierarchically group flat recipient recommendation lists in email such that the hierarchically grouped lists require less user effort than the flat lists in terms of number of lists scanned, elements clicked, and recipients manually entered. However, these results only apply to email. And there are some other applications in communities or other message-based systems that may use our approach to address multiple recipients. For example, in Stack Overflow, users have to assign tags to be associated with certain questions. And it may be helpful to treat these tags as recipients and use recipient prediction to suggest additional tags users may find helpful, which the users can then select and then add to their question. So we first tested this using a flat-based approach. And we saw that subset-based required more manual entries, meaning that we judged it to be higher cost than an intersection-based approach. So recall that the driving force behind the development of our hierarchical approach was that subset performed better. This then indicates that our hierarchical approach may not be as successful in this case. And in fact, we saw just that, because hierarchical required the same effort as flat. And we see this because the A value, or average accepted recipients per click, was much closer to 1. So indicating that users didn't tend to accept more than one recipient with each click. They didn't select our groups that we presented. Therefore, we judge hierarchical to not be better than flat in Stack Overflow. And upon further analysis, we determined this is likely because Stack Overflow forces a strict restriction of at most 5 tags per question. This means the hierarchical is not as helpful for building these large groups of tags for each question, and there aren't large groups of tags in past messages to construct a larger hierarchy that is useful for making future predictions. So, okay, so we're replaying messages. So we're treating the messages as ground truth. And if we assume when they manually enter recipients, they would enter according to the order that they're in the message, where they first address the to, the CC, and the BCC. And then we assume they would select the largest group from the messages, or if there's a tie, it's whatever's first in the list of recipients, suggested recipients. Right, exactly. So yeah, so it's all deterministic in terms of the data set we have. Sorry. We then looked at Usenet. Some of you may not be familiar with Usenet. Usenet is a forum system where you send posts to news groups or forums. And it may be helpful to address news groups then as recipients and suggest additional news groups you may want to send a post to. So we'll look at flat-based approaches again first. And we see that subset-based required fewer scans and clicks and about the same manual entries. So because subset-based is better with respect to scans and clicks and about the same with manual entries, we judged to be better. And again, because subset-based drove the development of our hierarchical approach, this indicates our hierarchical approach may be successful here. And in fact, we did see that, where hierarchical required fewer scans and clicks and about the same manual entries. So again, we judged hierarchical to be better than flat in Usenet. And this actually, upon further analysis, this supports our second claim as well, because there's no such restriction on the number of news groups for any particular Usenet post. Some posts contained as many as 18 news groups that a single post was sent to. So I think it was, yeah. So in terms of absolute value, absolute difference, that because we were looking at whether it was less than 1, so that was the absolute judge. So let me see if I can point out. So yeah, so this is, so required fewer scans and clicks right here, and about the same manual entries. And this, are you talking about this case right here? Yes. Yeah. Right. So this one, sorry, the intersection-based is compared to this intersection-based, and subset-based is compared to this subset-based. So we group those hierarchically. Does that make sense? So that's what we're trying to compare. Oh, really? Mm-hmm. Yeah.
Did you actually define scalar weights for each of these columns, A, S, C, and M, to reduce this to a single value?
We did not, because we wanted, yeah, so they're all different dimensions of effort. So we didn't want, so we ranked first on different, so we ranked in terms of manual entry and that sort of thing, but we didn't combine them into a single. Okay. So based on those findings, it's possible to generate hierarchically grouped recommendation lists for addressing recipients in Usenet and Stack Overflow, such that they will require the same or less user effort than flat recommendation lists, and less effort than manually addressing recipients in terms of scans of recommendation lists, selected recommendations, and manually entered individuals. So we've now added into this space of our timeline of recipient predictions. In particular, we found that flat group-based recipient prediction, we provided support that they're helpful in email, Usenet, and Stack Overflow. We've provided support that flat subset-based recipient prediction is even more helpful in email and Usenet. And hierarchical recipient prediction is even more helpful in email and Usenet. So going beyond just recipient prediction, what we're really doing is generating ephemeral group recommendations, where for each message, users are building ephemeral groups of recipients that they're sending a message to, and we're helping users build that. So in some cases, it may be helpful rather than creating a new group for each particular message, it may be helpful to generate persistent groups across multiple that can be used across multiple messages. So to do that, we'll generate persistent name group recommendations. So what are name groups? Get some water first. Well, name groups are semantically labeled groups of users with whom to share information. For example, you may have a faculty search committee which contains many members. And this is typically made before a user performs a sharing action, such as sharing some piece of information. And then that group can be used in those future sharing actions, such as setting privacy rights for some shared survey about a faculty candidate, or in the current state of the art in Gmail, this name group can be entered as a recipient of some email message. The system recognizes that as a name group and replaces it with the members of that group. So why should we use persistent name groups? Well, based on the previous finding that it's likely easier to remember and use a group than individuals, it might be easier to use these name groups than individual recipients. And they're also supported in many systems, such as Gmail, Mozilla Thunderbird, Facebook, and Google+. And however, there are certain problems with name groups. Namely, Passwork has observed that users do not create name groups in Facebook or Gmail. And Passwork has observed that groups should change over time, but keeping multiple name groups up to date has been stated as an open problem. So there's really two types of recommendations associated with name groups. Foundational, which recommend which name groups to create, and evolutionary, which recommend how existing name groups should evolve. And we'll first address foundational recommendations because you can't evolve what hasn't been created, so we'll first help users create these groups. And there is some work in this area, and most approaches have focused on structure-based mining, where users are sorted into user graphs. So for example, in Facebook or communities domain, these are based on specified relationships, where users in the graph have edges between them if they have certain specified relationships, such as friendships. Or in email, we may use co-occurrence and collaborative actions. So individuals in the graph are senders or recipients of past messages, and edges exist between them if they exist together in past messages. And as more messages are seen, more nodes and edges may be added to the graph. From these graphs, groups are extracted by identifying initial structures, such as clicks or triangles, then splitting those structures or merging them with additional individuals or groups. And based on these approaches, we see there's some similarity across both systems and domains, and that suggests some cross-application is possible. And this was our goal. And to do that, we first looked at all the different approaches in different domains. So we saw there were many different approaches in Facebook or the communities domain, but there was only one approach that we knew of in the email domain. So because of this imbalance, we wanted to cross-apply from Facebook to email. And in fact, if we're able to do this, we may be able to apply these approaches that are helpful in Facebook with specified relationships in other community message-based systems which don't have such specified relationships. So to do this, we needed to first infer relationships between recipients from past messages. And we did this in 3 ways: looking at co-occurrence only, or we looked at co-occurrence but ignored all old messages older than some threshold, or we ignored all relationships whose messages yield an IR score below some threshold, where IR is that equation I talked about earlier. And then we built a relationship graph from these inferred relationships and predicted groups using a past approach from Facebook. In particular, we used the Bacon and Duan approach from 2010 because we had access to both the reasoning and the source code behind this approach. So our next goal was to evaluate this. And in order to do that, we needed metrics. Well, we used the percentage of recommended groups that are accepted, which is, and we accepted groups if they were helpful or reduced the cost of addressing some future message. And we measured this as good if it's greater than 0, which means at least some of our recommendations were accepted. And we also measured effort to address each future message, where effort was measured in terms of relative additions, or the percentage of recipients that must be addressed manually, and relative deletions, or the percentage of group members that must be deleted. And we judge these both to be good if they're less than 1. Because if they're less than 1, that means users don't have to add all recipients manually and don't have to delete all group members for each group, for each message. Sorry. We then evaluated these in 3 different systems: in email, with data collected from an email web app in conjunction with an RAU Andrew Gabriel; in Usenet, using a public data set, 20 news groups; and Stack Overflow, using the Stack Exchange public data dump. In email, we found that ignoring messages older than 1 month worked best. In Usenet, we also found that ignoring messages older than 1 month worked best. And in Stack Overflow, we also found ignoring messages, but the threshold was different, where the threshold was 2 years. And in each of these cases, we found percent accepted to be significantly greater than 0, and relative additions and deletions to be significantly below 1. However, I would like to point out that Stack Overflow has a slightly low, or pretty low percent accepted, even though it's greater than 1. So that may yield some frustration in users, which causes them not to use recommendation schemes in the future. We didn't evaluate that specifically with our metrics, though. So based on these findings, we have our next two sub-theses. It is possible to cross-apply foundational name group recommendation approaches from Facebook to recommend groups of email addresses in email, such that some recommendations will be accepted, and the use of the accepted recommended groups in future messages require less effort than if no such recommendations have been generated. And rather than read out this whole long sub-thesis, it's actually the same as the first, just with email replaced with Stack Overflow and Usenet. So these show that our cross-application approaches are helpful, but to use these approaches, users must know that when to trigger recommendations. And determining when to generate recommendations can be difficult. So for example, let's assume some user Alice wants to create a group, CS study group, which contains David, Ava, Bob, and Chris. So when should she create this group? There's a whole bunch of time points at which she could do this: before or after a computer science class begins, before or after she sends her first message to this group, before or after she receives her first reply to this first message, before or after the computer science class ends. And you can imagine in reality there's many more messages, many more events that make this decision even more complicated. And past work has observed that users don't properly use name groups to begin with. So that means it's likely that users would not be able to correctly determine when name groups would be helpful. So to address this issue, we developed a Bursty model, which is based on the idea that new messages may indicate bursts of change in the relationship graph. Then change in the graph indicates that new groups may form. And new groups that include the new members, or the members added by these new messages, in the burst of change should be recommended because they're triggered by this burst of new messages. So to evaluate this, we sorted the messages from each data set into a timeline where the first message and the last message denoted the beginning and end of that timeline respectively. We then allocated the last 20% of messages for evaluating the use of groups and not the prediction of them. Then we could use non-bursty predictions just before this last 20% of messages. And we could use the 40% of messages just before this last 20% to generate bursty predictions. We then could compare bursty and non-bursty approaches using our past metrics we'd already used: percent of recommendations accepted, relative additions, and relative deletions. So we evaluated again using our three data sets we had talked about earlier: email, Usenet, and Stack Overflow. And we see that all bursty approaches reduced addition and deletion costs, and they're denoted in green. But only in email and Stack Overflow did the acceptance rate increase. And in fact, in Usenet, it decreased pretty significantly. And in email, we did not pass the t-test, p less than 0.05, that bursty costs were less than or equal to their cross-application costs. Oh. The same time window? Oh, yeah. So I used the best performing approach from the cross-application and used that to generate the bursty groups. So that way I could, if it doesn't perform better than the best cross-application approach, it's not better than it. So, and so we couldn't say that email, while email works better in this particular case, we couldn't say this is general for any other sample or data set. So this gave us our next two sub-theses. It is data, in our data from our user study, recommending the bursty creation of name groups in email based on seeds from collaborative events will be reused more often and require the same or fewer additions and deletions than if they were created using past name group recommendation schemes. However, it is not clear that such results will apply in other data sets. And it is possible to use bursty name group recommendation in news groups and Stack Overflow such that some recommendations will be accepted, and the use of accepted name groups in future messages require less effort than if created using past name group recommendation schemes. So let's assume for a moment the users are able to correctly create groups in the correct time frame. Maybe my methods, maybe something else entirely. And as previously mentioned, past work observed that groups change over time. So for example, Alice's study group containing David, Ava, Bob, and Chris, she may send out an email to this group and some additional members, John and Katie, welcoming John and Katie to the group. So she'll want to likely evolve her study group to include John and Katie. So how can she do this generally for all groups that she wants to evolve and correctly? So there's different methods she could use to do this. She could do a naive approach or manual evolution, whereas other users are added or removed from the user graph. The user evolves those groups using no additional tools. And this is good in that it requires no additional computation from the system, but it requires user effort to determine which groups should evolve and how. She could use past methods or full recommendation, or foundational recommendations are used to generate a whole new set of groups, and the old unevolved groups are thrown out. This is good in that users are not required to know which groups should evolve, but users will likely have to reproduce previously performed actions because they're constantly interacting with new foundational group recommendations. They may have to reproduce accepting, editing, or rejecting recommendations. And we could use a new method or change recommendation, where a tool recommends which name groups should evolve and how. And this is good in that it may be able to remember users' past actions, meaning they don't have to reproduce them. But it may require the creation of new, possibly expensive methods or models. And our approach was targeted towards this change recommendation approach. And there are some instances of change recommendation in past work. However, these are limited in that they either require users to know which group should evolve and when, or they are limited to most 2 groups. So our goal was to improve upon previous work by developing new methods that do not require users to know which groups should evolve and when. And this means it's reduced user effort. And no restriction based on the number of groups, which means we can apply to a wider range of systems which have unspecified number of groups. So our approach first generate new foundational recommendations using an existing approach, meaning it's composable with past successful foundational recommendation approaches. We then match and merge recommendations with existing groups based on the change in the social graph. Then these merged results serve as evolutionary recommendations, the merging of the recommendations with the existing groups. And we tested these in 2 types of systems. Explicit graphs, or those based on specified relationships. And we tested in 2 Facebook data sets. And implicit graphs are those where relationships are inferred from past messages. And we tested in our previously described data sets of email, Usenet, and Stack Overflow. In the explicit graph case, we found that we reduced both additions and deletions when less than 50% of the nodes in the graph were newly added. However, we did not ever show any significant improvement over a full recommendation approach in the implicit graph case. So we've now added more to our timeline of persistent name group recommendations, where we've shown cross-application foundational recommendations are helpful in email, Usenet, and Stack Overflow. We've shown that the Bursty Model can be helpful in email and Usenet, and that the evolutionary approach is helpful in Facebook. So finally, we want to address this last bit of the timeline. And to do that, we consider the fact that we are looking at multiple groups that users may have to deal with. So users may have to deal with alternative group selection, or in other words, multiple solutions to a user selection problem. And ultimately, users decide on one group of users with whom to send some information. And they may decide on this solution based on certain goals. So for example, right here is an email about filling the last meeting slots for a faculty candidate. And this may have been decided based on, are these appropriate recipients or expert detection? Can these recipients actually adequately evaluate this candidate? Will I get an answer that I need, sufficient answering? In this case, we need to know that at least one of these people will say, yes, I can fill that meeting slot. And finally, we need to make sure that they will receive a response in time, or response time. We'll make sure I get a response early enough that I can schedule this meeting and let the candidate know. So there's been some work in addressing goals. Namely, there's been work in predicting expert detection, predicting sufficient answers. But when we started this work, there was no actual work in predicting response time in email and communities. However, there was work in providing links between features and response time. So we wanted to go beyond this. And these were the works that were working on that. And we wanted to go beyond this by using these features to provide response time predictions. And as we were working on this, one work of contemporaneous work was published on response time prediction in communities. However, this work required features that needed to be extracted manually. For example, the difficulty of a question that was asked. And so we wanted to go beyond this and used features that could be extracted automatically. Namely, use the sender of some message, the recipients of that message, and the words in the title of that message. So we then targeted our predictions towards Stack Overflow. And the reason we did this is in Stack Overflow, messages are typed, where certain messages are questions, some are comments, and some are answers. And the response time in Stack Overflow can be defined as the time from the question to the first answer. This is not the case in some other systems, for example, email or Usenet. We might have questions, but we haven't typed them to specify that, and they have responses that may be comments, maybe answers, maybe something else entirely. So we didn't focus on this to start off. And we used, to predict response time, we considered 3 methods. We used a prediction based on distributions of response times in our training data, which tried to predict based on the distributions we saw. Then we gave a range of time in which a response is likely. And this, we use clustering to do this, where we allow non-arbitrary response time ranges. For example, one cluster could be from 1 minute to 10 minutes of response time predicted, or cluster 2 could predict response time of 1 week to 2 weeks. We also looked at treating response time as a popularity metric, where more popular messages would receive faster responses, and then we try and predict messages' popularity. And to do this, we looked at collaborative filtering, because this has already been shown to be effective in predicting popularity in content, such as films on Netflix. And these were applied at different times. The distribution was done with an REU Preeti. The clustering approach was done in Vladimir's course, and the response time was done in Alex's course. Or the popularity was done in Alex's course. So because I know it's a little bit long on time, I just go into the best approach right now. And collaborative filtering performed best where 62.9% of predictions were within 1 minute of the true response time, which is excellent. So this gave us our final subthesis we'll be discussing today. It's possible to use collaborative filtering to predict when Stack Overflow question will receive its answers, and such that the predicted response time will be closer to the actual response time than random predictions, distribution-based predictions, or predictions made using k-means clustering. So we filled in this last little bit of our timeline, and we can actually see many approaches that we filled in this with, and some of these are applicable across both systems and domains. And this application across both systems and domains implies there's some similarity in information sharing patterns across these systems and domains. We've also made contributions in terms of tools that we've designed and implemented. I've already mentioned the email thread data collection tool. There have also been Facebook group data collection and email interface testbed, which are not discussed here today, but I think are in the dissertation. We also can sort our approaches in terms of a design space, where the columns are systems that we've tested our approach in, and the rows are approaches that we've used. Checks mark that it was successful there. X's mean it was not. Blank means we did not test it. And one question mark indicates it was not statistically significant, so we don't want to make too strong claims about that. And we can see in here that some approaches some systems are closer than others, where success or failure in email or Usenet tends to imply the same, where other cases don't match as closely. And there's empty spaces that future work can attack or go further in depth to, such as providing statistical significance in the email case. We can also future work can also address certain questions that our work motivates. Namely, are our approaches applicable to other domains or systems? Some approaches, such as those suggested, some systems, such as those suggested by Stanale, are distributed file systems or virtual worlds or multiplayer battle arenas. In each of these cases, users must form groups of users. You can form groups to share files or folders with in distributed file systems, or you can form groups or guilds in the other case. You also select recipients of shared information. Distributed file systems, you choose with whom to share some file or folder. In virtual worlds or multiplayer battle arenas, you choose who to invite to some match or game. And in fact, there are different prediction algorithms in some of these systems that might allow some cross-pollination with our approach to build even better prediction schemes. There's also, we want to know, are there better metrics for measuring effort? Past work has observed that pupil size and blood glucose level is highly linked to the mental load of participants in studies. So those might be good measures of effort. Moreover, we only measured whether users scanned, clicked, or manually entered or switched between mice and keyboard. So it might be helpful to also measure the time it takes them to actually complete those, which some past work has also done. We also wonder whether content can be included to make recipient prediction or maybe other predictions better. We only indicated that a specific method from past work was not helpful or was not better than group-based approaches. But we're hopeful about other methods, such as automatically identifying templates of messages, classifying based on those templates, and then providing appropriate predictions. We also want to know, can our name group recommendations serve purposes other than addressing future messages? For example, past work has identified that name groups can be helpful for understanding social structures or inferring or specifying profile information. So it would be helpful to see if our predictions are helpful for those cases. We also want to know, will people place undue trust in our predictions? Will they select predictions even though they're incorrect? And this, in other domains, this phenomenon of risk homeostasis has been observed, so maybe it applies to our domain as well. Finally, we would like to move towards a possible combined approach, where maybe we can predict persistent name groups, ephemeral groups, and response times altogether. And here is a mock-up of some hypothetical approach we've come up with, where recipient completion can predict not just individual recipients, but persistent name groups and ephemeral groups, each of which has an assigned predicted response time. Or after an individual has been fully entered, maybe we also predict persistent name groups or ephemeral groups as completions, which also have their own predicted response times. And finally, I'd like to end with some acknowledgments. My committee for all of their insightful comments and feedback. It's really been helpful and made my dissertation much better. My advisor, Pursuin, who has taken me on since freshman year of undergrad and helped me guide me through this. All my sources of funding, I was a TA under Steve Weiss in fall 2009. My NSF grant, I've been a TA under Jay for the past 2 semesters, and an alumni fellow. I also would like to thank my RAU collaborators, many of them who have worked on projects specifically detailed here today. Also, the 2 graduate members of the Collaborative Systems Group, Jason and Mauro. All of the faculty in the department, because I've been here 9 years, had the opportunity to study and learn from many of you, so there's too many to name. That same vein, there's so many friends I have, some of whom are here today, that I really am appreciative for, and I hope you understand I can't name you all. And in particular, I'd like to thank my wife and my parents who are here today, and then my brothers and sister who can't make it here today. So with that, thank you, and open floor for public questions, I guess.